Refresh. Okay. Hit the live. Oh, there we are.
What?
We're online, are we not?
No, no. Yeah, we are online.
We're live. I'll stop talking.
Wait. Yes.
Okay.
And we have video. Whoa. So apparently, all we had to do was just be patient, which is literally the one thing
We have none of.
that I am incapable of doing. So this is really cool. Look at this. We're just like side by side.
I can see nothing but a frozen version of my face looking suspicious.
Does she get a video
okay.
camera out?
There we go. Should be fine.
Now she can see. Right? Now you can see in the
I
the
still
Zoom?
see myself looking deeply suspicious off to the side.
Maybe you turned her video. Oh, yeah, boy. That's hilarious. How about
Okay,
now?
now I can see.
Now you can see us? Okay, all right.
Yes, this is much better.
Oh, God. Computers are hard. How's it going, Pamela?
It's going well. I am
been
out
so
of
long.
coffee because it took us so long to get started. So I'm sitting here with my empty coffee.
Yeah, it's I'm clearly maybe I'm over caffeinated. I'm not really sure. We're juice up on adrenaline at this point as we attempt to do new things. That's the downside of being an early adopter is, the technology gets a little difficult to work with and things go wrong, but we push forward
It's
all
true.
the time. So so someone says that Pamela was frozen, and then someone else said no, Pamela wasn't frozen. She was just staring.
I do that sometimes, but usually not quite that stilly.
Glaring. That's it. Yeah, she was just glaring. Yeah, the screenshot. I guess what had gotten captured for what you were saying was pretty hilarious. So you're very looking furtively and suspiciously to the side. Yeah. So now we got a split screen, but we don't have to just have a split screen. We can have just me, and we can have just Pamela. Look at that, and it's all thanks to Chad, who is right there. Push them there. You can see we're attached by headphones. All these little things we got to figure out how to improve. So we're gonna get headphones. Perpetual beta testing. We also have a bunch of really spiffy pictures lined up. So I think this is gonna be a better experience for those of you who are watching. So let's get a couple of things ready to go for me. Now, have you got any more interesting trips and stuff coming up, Pamela?
Next week, the reason we're recording a doubleheader today is because next week I'm going to be in Medellin, Colombia for the Communicating Astronomy to the Public meeting, trying really hard not to become patient zero with Zika for St. Louis. Our mosquitoes have hatched, so I'm sort of like, gah! So I have like lots of under 3-ounce containers of DEEP that I'm taking.
Oh, really? So you might bring Zika back to St. Louis.
I'm going to try not to. It's my goal.
So let's see if I can say hello to some people. Let me see. Whoa, there's a bunch of people. Okay, I can say hello to these people. I'm gonna say hi to Cosmic Shoebox, David Trogue, Galaxia, Graham Ash, sorry, Guido Bibra, Jerome Mooten, John S., Jorn Albert, Kurt Reber, Larry Beckham, Margot Robinson, Michael Jobin, Nancy Graziano, Nicole Gatnikar, Phil Wilcox, PsychoCat749, Richard Strazel, Sylvan Westby, Thomas Traniker, and Val DeGast. Hey, everybody. Welcome to the new and improved Astronomy Cast. We hope. So, are you ready to record this show?
I am, and I'm going to turn away from the chat feed on YouTube because it's deeply mystifying.
It's mystifying and also just addicting, and yeah, it's hard to.
We're
Look
being
away.
warned to watch out for hippos, and if a hippo manages to make it up to the second story of my house, something has gone terribly wrong with the universe.
Well, no, the hippos in Colombia.
Hippos don't exist in Colombia. They're African.
Oh, they do. Escobar had a hippo zoo on his property, and they've gone native.
Oh,
Yeah, yeah, and so there's a roaming group of hippos in Colombia that yeah that are
I
there.
doubt they're going to be in Medellin proper, however.
Yeah, well, maybe I don't know, but apparently the biologists are well aware of where they are and how many there are, and they're keeping a really close eye on them, and so it's not like it's going to be a problem with them kind of getting out and spreading. But apparently, it's a really good environment for them. They do really well.
We have wild parrots in California and wild emus and ostriches in Texas for similar reasons.
Yeah, yeah, exactly. Okay, so are you ready to press record?
I am, and okay, I
Yeah.
seriously have to like close the chat because now they're talking about hippos with syrup, and that's just confusing. Okay,
They're
I'm
just
ready to
mashing
press
so many
record.
Astronomy Cast memes together that you just can't handle it.
I can't. It's true. I'm pressing record.
Okay, I'm
Hi,
also going to press
Preston.
record. Hello,
Hi.
Preston. We got the right microphone. Okay, so that's how we record the raw audio. He says, telling Chad. Okay. And now I'm going to grab my intro, and then I'll give you this window back when I'm done with it. All right.
Sorry
Okay.
for the extra audio, Preston. We're trying new technology on the video side.
Yeah. All right. Ready? Here we go. Astronomy Cast, episode 414, Navigating Far. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Good. A little exhausted from the second show that we've done today, but this is what we have to do to deal with both of our busy schedules. Actually, last week I spent a big road trip traveling around Banff, Jasper. Just an amazing place to be. So if
All
you
the cool geology.
yeah, the geology and the wildlife. We saw bears, grizzly and black, elk. It was a really good time. And my wife, who comes from Texas, had never seen anything like this. So if you ever, if you have a bucket list somewhere, put this on the bucket list.
That sounds absolutely amazing.
Yeah. Okay, so in our last episode, we talked about what it takes to navigate across the solar system. In this episode, we scale things up and speculate how future civilizations will navigate to other stars and even other galaxies. So just to catch people up, Pamela, last episode, we talked about how, when you're here on Earth, we can switch back and forth to us as we go. Sorry, Preston. Sorry, as we last episode we talked about how navigating on Earth, we want to be able to know where we are, and we used to use the stars, and now we use GPS satellites. But it's a fairly simple thing, relatively speaking, because we're moving around on a two-dimensional surface, and sometimes you go into three dimensions as you go up and down in altitude. But it's relatively straightforward, and that to navigate inside the solar system, spacecraft use signals to and from the Earth using the Deep Space Network to calculate their distance from the Earth, and then we'll use other signals to be able to calculate their velocity as they move forward, and eventually you can get sort of a state of your position of where these spacecraft are and zip around. And we can imagine some far future where there's transponders attached to every asteroid in the solar system, on lots of planets, on even just floating in space, and you use this deep space network proper to be able to actually navigate around the solar system. So, Pamela, let's take this whole concept and scale it up one notch. What's it going to take for us to be able to navigate from star to star? Is there audio?
star, and that will give you your three-dimensional velocity.
Right. And so pulsars, right, are of course these dead stars, neutron stars, rapidly rotating. They're putting out these beams of radiation that are coming from them, and so they're so, I guess they're like these clocks, these really precise clocks. You can sense those signals and get that Doppler shift from them. And so you can tell your distance to all of these pulsars based on...
You can tell your velocity.
You can tell your velocity with the Doppler shift.
Mm-hmm.
Right, okay.
And so this gives you your three-dimensional spatial motion. And you need to have at least three of them, because if you only use two, that tells you what plane of the universe you're in. And plane is useful, but there's a whole lot of space in the other direction of space. So use three different ones to get at your three-dimensional location, or three-dimensional velocity, rather.
So do we do this right now?
Well, so it's part of our research on pulsars. We can study how they're moving relative to us, how we're moving relative to them. Some really neat research comes out of looking at these very high precision Doppler shift, where you have to start taking into account things like rock has tides too. And so the tops of mountains will move up and down, carrying observatories with them with the tides. It's not a lot, but it's enough. You have to add it into your calculations. We have to subtract out the Earth's movement around the sun. All of these different motions add up. But if you remove them correctly, it also allows us to do things like find masses orbiting around pulsars that are pulling the pulsars to and fro. And this is actually how the first planets, and by planets I mean small chunks of dead stuff, how the first planets orbiting other stars were found. It was found through the timing errors in pulsars, which should not be able to have timing errors. So you work it backwards and you get at these are Doppler shifts created by these small planet-like-ish things yanking to and fro on the pulsars.
But aren't we getting to a place where... I know, like with, was it Dawn, or maybe it was one of the previous missions to that it actually had the capability to orient itself to find all of these objects in the sky and then know where it was. So I guess that's,
So what it can do, and this is again getting at that other dimension which we talked about in the last episode, where spacecraft like Dawn that are in our solar system can use radio signals to figure out their distance from Earth, and that puts them on a surface of a sphere that has that radius. But then to figure out exactly where they are on the sphere, they take pictures of the sky, and those pictures of the sky give them that other dimensional orientation. So with pulsars, and pulsar observations are much harder than taking a simple image and figuring out your orientation. Once they go through and they measure the Doppler shifting of multiple pulsars, it would give a spacecraft its three-dimensional velocity. But then to start to get at its where am I in space, that's where you go back to taking images. But you have to take amazingly precise images that allow you to make out the slight variations in positions of the stars that are closest to you and the lack of motion of the stars that are most distant from you. So you have to have a working three-dimensional model, which is something we're actually working to slowly build up with the Sloan Digital Sky Survey, with Gaia upcoming, with Hipparchus in the past. We put all of these different pieces of information together along with the actual velocities of the stars to build a model that we can someday use to move through space. And today we can simulate moving through space in things like Worldwide Telescope.
Right. Do you think that the building the capability to spot and track a pulsar signal into a spacecraft is going to be something that's fairly complicated, or is it, are they fairly bright signals?
There are some that are fairly bright, and if you think about it, if you have a spacecraft that you plan to travel between the stars with, it should have the capabilities that a not too complicated radio telescope that Jocelyn Bell Burnell built in graduate school had. So that's the kind of technology that we're looking for, is the type of stuff that Jocelyn was building before we were born and using to detect pulsars. It's smaller now. It's easier to do. It's something that some lab classes do. It's just more complex than taking a picture. You have to turn your radio signal, listen for a little while, process that signal. It's something we can do today, but we don't need to do it today with our spacecraft.
What kind of accuracy can they get?
For the velocities?
Yeah.
It all depends on how fast the pulsars are rotating, but you should be able to get down, if you have good enough detectors, down to the kilometers per second and potentially meters per second. We don't currently need to do meters per second, but that's something that we do when we're detecting planets around massive stars. And so there's also if you're really wanting to get deeply engaged, there's all sorts of different ways to get at this information.
Right. And I guess when you're moving from star to star, and maybe it's going to take you years to make that journey, you're going to have a long time to be able to sort of better zoom in and really figure out the accuracy of where you are.
Right. And the more samples you take, the better your data is going to be.
So that's getting around around the local area, the local star system. How far would that be able to take you?
Well, you need to have pulsars all around you for this to be successful. So you need to be able to get those 3 not too far away pulsars, by which I mean you're embedded within the system. So within our own galaxy, as long as there's old population of stars within sight, this works beautifully. But once you get into the space between galaxies, well, pulsars aren't all that bright. So that's going to be a problem. But also you're going to have all the pulsars are in that galaxy that's now behind you. You may not be able to see the pulsars in the galaxy that's in front of you. So once you start exiting galaxies, you need to find that new standard source that you can use as your Doppler shift, basically network of distant objects.
I love how you casually talk about how you're going to be leaving your galaxy, being able to see, then you're going to have to start focusing on the next galaxy. And it really sounds like we somehow reverse roles here because, suddenly we're a type 3 civilization moving from galaxy to galaxy, spreading out into the entire Hubble volume of space that we can reach. So that's good.
But this is tractable. This isn't pie in the sky impossible. This is the kind of thing that once we figure out how to download intelligence into computers, and we aren't worried about only living for 70 to 100 years, this kind of exploring the universe becomes much more interesting.
Right. Once we've moved into our robot bodies and
exactly.
Yeah. But with the quasars, using quasars as navigational aids, they don't act in the same way that a pulsar does. It's not like they're putting out pulses on a regular basis, right?
No, but with quasars, you have this distant background. So when you're within our own galaxy, you're moving through these pulsars. So you might go from using one set of 5, because 5 is better than 3, to as you drop one, you pick up another. Well, as you start moving between the intergalactic space, quasars have extremely bright emission lines. And these emission lines that you get are a concrete line of this is exactly where the atom is giving off light in a specific wavelength that's a little bit smeared out because things rotate. And you look for that line to change how it's Doppler shifted. And using information about the expansion rate of the universe, the distance to these objects, their starting point for how they're Doppler shifted. And then you can get at how their apparent Doppler shift changes due to your own velocity and eventually due to that changing in distance between you and them.
Now, we've talked about using natural sources to be able to navigate yourself around the galaxy and eventually around the universe. But as with the solar system, we're going to want to put in some kind of artificial system. So are there methods that we could use? I'm thinking like neutrinos, or could we have, the equivalent of transponders, but at a star system level?
So the thing is that while within our own solar system, we really do want to eventually add these beacons, these transponders with known frequencies, with known orbits. The universe really does provide once we get beyond our solar system. The pulsars, we know how pulsars work. We know how they evolve with time. They don't have any hiccups or weirdnesses in general with their rotation. So they are beacons. They simply are. Now, quasars, you do run into the periodic problem, and Nathan Lowell wrote a great little short story on this. You do run into the periodic problem that quasars shut off, and occasionally new ones turn on. So occasionally your beacons die, and occasionally you get a new one, and you have to keep track of these things. But again, quasars, atomic spectra, they don't change. Hydrogen, it's perfectly happy to have its Balmer series, its Lyman series. And by keying in on those emission lines, those are our beacons. We don't need to build any intergalactic megastructures for navigation. We can just happily build them to live in, because why not?
Now, we've already actually sort of used this navigation system with the Voyager spacecraft, right?
We've used it to help people understand how to find us later.
Right.
Where
to send the invasion fleets.
Exactly. So things like neutron stars, we know their size. We know how much light they're capable of giving off as a function of temperature. And so if you look out at a series of pulsars and you measure their timings and you rough out their distance, well, this image on the plate that was on Voyager marks out where we are relative to a series of different pulsars. So theoretically, the alien who someday scoops up this plate and has interstellar travel will be able to come visiting. I'm not sure how I feel about that, but for better or worse, over the fullness of time, we do get carried away from these pulsars. Quite literally, we get carried away through orbits.
Right, but as we know, the Earth has been broadcasting the existence of life with its atmospheric gases for hundreds of millions of years. Mm-hmm. So any aliens capable of tracking down, finding the golden record on the Voyager spacecraft, and then being able to use that to trace its way back to us, this is going to be old news to them.
Probably.
Like as if it's an old timey record, but it was great. It's great that they use that as that was a Sagan suggestion, yes. Right? Yeah, yes. Carl Sagan suggested that they build this record, and it's great because it's just got this pulsar map that just tells you which star is the sun and where to come to steal our water.
Go look at that third rock.
Yeah.
And that's where we are. So we'll be safer once we get to Mars.
Right. They won't even know. They'll go to Earth. They won't even see us. They'll go to Mars, or they won't even see us here on Earth, and we'll be set. So, what about like course corrections and things like that? Because the speed of communicating, as we understand it right now, is really limited by the laws of physics. So if you're going to attempt to communicate with your spacecraft, which is moving along this vector, the spacecraft may know where it is, but as that spacecraft gets further and further away, you're going to have a longer time to communicate with it. And if it's going faster, then relativistic time delays start to come into play. So how will that all come into the picture?
This is something that Orson Scott Card, say what you will about other things, he got the science right in Ender's Game, where characters who were moving at near the speed of light, who moved between solar systems, essentially skipped through time. And you'd send out a burst of communications and then wait days, weeks, months to receive that slow message that then your computer reprocesses to normal speed.
If I remember, they used in his books, they had a method of communicating faster than light speed.
That came in later where they developed the Ansible. But initially, when
Right.
they were speaking to their general, it
Yeah.
was all through horrific time lag.
Right, so you would be getting slow motion or sped up, depending. I guess both people would see. I'm trying to remember how this works, but you would see slow motion from the other person because there was a difference in your velocities, and then you would have to then speed up the video and the audio to have it look normal.
Right. So the person who does the accelerating will appear to be significantly slowed down. And then the people who didn't do the accelerating, who are back on Earth, will appear to be extraordinarily accelerated. So if we're here on Earth listening to the signal from the astronaut, it will be this high speed machine on fast. It will be this greatly slowed down, like your dying batteried Walkman from the 80s, whereas the signal that they'd receive from us is this high-speed buzz of a machine on fast forward.
Yeah. And then I guess the further you get, you have to take into account the transmission times to be able to reach them, then I guess the amount of time based on relativity on how fast they're going compared to you to be able to understand and formulate a response to it, or to make a course correction or whatever, and time to communicate back.
And once you start getting far enough from the planet Earth, once you start reaching cosmological distances, you have to also take into account the rate at which the universe is accelerating. So you have their velocity, you have the velocity of the universe carrying them away, and all of this adds up to math. It all adds up to doing lots and lots of math. But it's stuff we already know how to do. Ned Wright has an excellent website that explains a whole lot of this and has Ned's cosmological calculator on it that can do these kinds of calculations in a fairly straightforward manner. So we have all of these different things. We know how they work. But the real issue is you end up with a separation of society, a separation of culture, as the two societies, the accelerated and the non-accelerated, drift apart through time, just as they just drift apart through space. This also came up in the movie last year that Kip Thorne advised on, where they got far too close to a black hole. I'm blanking.
Oh, Interstellar?
Interstellar. It also came up on Interstellar, this way you drift apart in time. Now, we do have some hopes for faster than light travel. It's unsure if we'll ever be able to actually harness them, but the entanglement of different particles that are generated together, we know that if you mess with one particle, you're also messing with the other, even if they're separated by vast distances. We don't know if there's a way to control that, but it's currently our only hope.
Right. Yeah, that the way, I mean, if I understand right, I mean, the entanglement causes it to collapse instantaneously, but you still require the speed of light to be able to communicate with the other party to find out what they saw. And so at the end of the day, you're both kind of stuck by the speed of light. But you can imagine, but so it's funny. It's like we could do the calculations now to control these vast space fleets and redirect the Earth defense fleet to Alpha Centauri as needed, except that we don't have the technology to make the Earth defense fleet go, nor necessarily the power to be able to send those kinds of communication transmissions those distances to moving targets and so on. So we can run the calculations, and then we could just wish that we had an Earth defense fleet too.
But you know, given the choice of having the technology and not having the math, or having the math and not having the technology, we're doing things in the right order. And it gives us room to dream, to imagine, to drive us forward with pathways of, we just need to develop the tools to do this thing. And science gives us a direction to head in. And then the engineers and technologists, they're the ones who eventually get us there.
Yeah, yeah. So is that it? This is a two-parter, navigating around the solar system. I guess if we find some kind of idea about parallel universes, then we'll have to figure out how to. Then we'll come back with
Well,
a third show.
I think we do need to add one more thing in. So we talked a lot about how we can know our three-dimensional velocity, but knowing how fast and in what direction I'm running only helps if I know where I start from. Google Maps needs to know my starting location, or it really can't get me anywhere. So when it starts coming down to figuring out where you are in space, we hinted briefly at you take very careful images, measure the positions of the stars, look for the parallax shift of the nearest stars and the lack of shift of the most distant stars. This is Star Trek's astrometric lab. But you can also start to get information from things like we know certain stars have certain absolute brightnesses. We measure the differences in their apparent brightnesses. And just like we can get at how far away a motorcycle is by how bright its headlight appears to be, we can get at how far away the stars are. Now you can extend this out and use some of the brightest stars in the universe to get between your nearest galaxies. You can use supernovae, however fleeting they may be, to nail down this galaxy is in this place, this galaxy is in this place. So it's much harder to get at the exactly where I am once you exit our galaxy, but we have starting points of how to do it.
Well, then I think until we can actually get those parallel universes figured out, I think we'll have to wrap up this and make this purely a two-parter, and it won't be a three-parter yet. But
that's okay.
Yeah. Cool. Well, thanks as always, Pamela, and we'll talk to you next week.
It's my pleasure.
No.
And now we save.
Wait. No, we keep the show going. So.
Sorry, this is where we pause to save the audio.
Yeah, so we actually stick around and answer questions. That was close. Chad just about shut down the live stream.
I was waiting for you to go ahead.
Yeah. So I'll save this one locally. That's episode 414. So go ahead. People who are like, I don't think you guys are going to be answering questions. And we are.
Yeah, no, we're
It's
good.
all part of the plan. We got it. We're ready.
We're not going to answer them for a long time because I have a dog to go shove pills into.
Okay. All right. So go ahead and put any questions that you might have in the chat, and we will take.
And if you use the question mark emoji, we can find them better.
Yeah, that's an easier way to do it. There was a question earlier up that came by. So Richard Straussel saying there's a great anime called Voices of a Distant Star about a girl who goes off to fight a war with aliens, and it's all about her communicating with someone that she left behind.
Okay, I'll have to look for
I
it.
haven't seen that. Let's see. Is there anything else?
G-Man 351 has the most depressing statement. Humans will never live anywhere except Earth. This planet was built as a prison. Look what happened when we went to that moon.
Yeah, I mean, we talk about what it's going to take to be able to travel to other worlds, and it's going to be our robots for a long, long time. I mean, there's some really interesting technology with the Star Shot.
So I write for Mother Zeta, which is a science fiction magazine that they get nonfiction writers to periodically write for. And I just read a preview story that I'm going to write an accompanying nonfiction for that dives into concepts related to downloading of the human mind. And this is something that crops up also in, I think it's God by the Numbers or Calculating God. There's a whole lot of different books and stories that get the idea of eventually downloading the human mind into computers. And if you can achieve that, then we just leave our biology behind. And it changes how we explore. But the question is there something about the human body that allows consciousness to work in a way that we may not be able to capture in solid state because it only currently works in wet state and we can't simulate wet state enough?
Yes. I mean, this is the argument that people are talking about right now, that when we simulate or when artificial intelligence is created, will it be by extending and being based on human intelligence, or is it going to be something completely alien that's cooked up in on the computer and has nothing to do with us? So so Margot Robinson wants to know, does your dog's medicine come in liquid form?
No, and unfortunately it doesn't, and it tastes truly hideous. I have to admit, I did the Serena Williams thing. I licked my dog's pill to find out why she was rejecting it so much.
Right, and it was awful.
It's awful. It's a human medication, but they don't coat the really small dose pills. And I'm going to go out and buy a thing of honey because I thought I had honey and I don't. And I'm thinking if I put the pill on a small cracker, coat it in honey, and then dust it with granola, that she'll hopefully not get it stuck in her mouth and not taste the pill until it's far too late. I tried spicy mustard between Weekly Space Hangout and this recording, and I'm now wearing spicy mustard on my blue jeans, and ended up simply shoving the pill into her mouth covered in spicy mustard and holding her muzzle shut. And I hate doing that. I really hate doing that. But she felt much better 20 minutes later.
So we got a comment here. Let's see if we can do this. There we go. Look at this. What if
that's
the
new and
computer
cool.
gets a bug? This comes from John S. Although I have no idea what he's talking about. Which computer?
What if we download our consciousness into computers and then the computers get a bug? So different science fiction authors handle that in different ways, where essentially you're creating mental disease in the humans that are in the computer.
Yeah.
It's terrifying.
Let's see. There was a question here. Cosmic Shoebox asked, what are your thoughts on cryogenic freezing for long-distance travel across the universe?
I think that the flaws in cryogenic freezing, the from cosmic rays to everything else knocking out bits of the human body, I really think that figuring out how to download the consciousness may actually be safer. But there are great strides being made in cryogenics, and if you're not freezing for the whole trip, if it's shorter periods of time where cosmic rays are less of an issue, it probably has good potential.
Yeah. It's tough. I mean, they've made some really interesting advances in cryogenic freezing just in the last couple of years. There's been some big updates. I guess it's like your last best hope of trying to make the meat go from one world to another. But I think that at the end of the day, it's going to be our robots. Or, we talked about generation ships. You take an asteroid, spin it up, make it travel for hundreds of thousands of years to get to another star system. That, and I guess eventually if we can get power, then we can get some actual relativistic travel going. But even that's going to be pretty tough. But I don't know. I'm looking forward to seeing what happens with the star shot. I think it's the star shot, right? Where they're going to be, they're going to be zapping little probes and moving them around the solar system. That'll be really cool to start seeing if you could scale that up. In the last episode we talked about, could we have some kind of solar system wide transponder system, but imagine if we had some solar system wide laser zapping propulsion assistance. And so you're going to be flying in your solar sail, and then you're going to go past one of these systems, and it's going to zap the laser and help you move in a different direction. And so, help you travel from world to world. You can imagine that being the future, is that the whole solar system is going to be filled with all these lasers, and they're all zapping people's solar sails, right?
Kim Stanley Robinson's book, Seven Eves, goes into that. And you run into the issue with that of what if there's a crisis on one of the worlds and their laser goes away? You might end up crashing, and death is bad.
Right. But space is,
not Seven Eves, Aurora.
Okay.
Kim Stanley Robinson's book, Aurora.
Yeah,
Sorry.
I mean, we've talked about how terrifying and really relentlessly space is trying to kill us all. So, that's just another way. Here's Dad, just put it on the list.
So sometimes we try and kill ourselves. Sometimes the universe tries to kill us. Having the lasers fail would definitely be us trying to kill ourselves, but not on purpose.
So, Elad Avron has a great question. Isn't the expansion of the universe invisible to us? So, isn't it space-time expanding? Would that expand the signal?
Yes, it totally expands the signal. This is why the cosmic microwave background is microwave instead of ultraviolet. The expansion of the universe actually expands the wavelengths from the most distant objects. So it's not just the velocity of carrying them away, it's also the expansion that is expanding them, and it all adds up.
Right. Well, because we talked about how, people always wonder, like, why isn't the Milky Way expanding? And because the objects in the Milky Way are gravitationally held together, right? But with the signals, just the pure electromagnetic signals that are coming from the base station on Earth or the pulsars or whatever, that is getting expanded with the expansion of the, it's not like it's being constrained by gravity. So it is expanding with the universe as it expands. All right, we'll take like one more question and then why don't we wrap things up for this episode? So, this is a toughie. Lazio Zjarto asks, how many course corrections would a spacecraft like Rosetta have to make before arriving on target?
It depends on the kind of orbit that they use. So you have to first of all shift your orbits. It totally depends on the orbit that gets used. And course corrections may be the wrong way to say it, because course correction implies they're not quite going where they meant to be and they have to fix it, which does happen.
Right, they're all planned.
Yeah, and so you do occasionally get different effects caused us to not be quite where we thought we were going to be. So there's a small course correction, but in general, it's planned firing of the engines to change orbits.
Yeah.
Rosetta is nowadays constantly changing as it zips back and forth, co-orbiting along with the comet.
I remember, like, with Curiosity and stuff, they make like 3 or 4.
It's not that many.
Yeah, burns over the course of it. And so often, they try to get their first insertion right from leaving Earth orbit, and then they will narrow in and make another burn to just get it even finer tuned in. And so they're really right on target when they get to the destination. And then sometimes they'll do a final, but I mean, often they're aimed perfectly to skim right into the Martian atmosphere or whatever. But as you said with Rosetta, right, they're going higher, they're going lower, they're working to try and get more and more science. And so a lot of the course corrections that Rosetta is making now, and same thing with Dawn, they hadn't necessarily planned these in advance. And so they're looking to get as much science as they can before they have to wrap up the mission. And I guess, I don't know, are they going to crash Rosetta into the comet in the end?
I don't think so.
Just going to stay orbiting for a while, yeah. Yeah, because I mean, the reason why they crash Cassini in the end of its mission is they don't want it to accidentally run into one of the icy moons and pollute it with
and there's really
life.
no reason to, there's not life on Rosetta, so.
Yeah. So why don't we wrap things up now? So 2 things. One, where can people find out more about you and what you're working on right now?
So most of what I'm doing lands on cosmoquest.org, but it lands in all sorts of various places. So follow me on Twitter and follow CosmoQuest X on Twitter, and you'll get all the links to all of the good stuff. Big changes are coming this summer, and next week I will be live tweeting from the CAT meeting down in Medellin, Colombia, where I shall be wearing all the DEET. All of it is going with me in small bottles that are 1 ounce each.
Right, because you can't carry that much on the airplane. And bring your hippo repellent.
I will do that.
That would be good. Cool. All right. And of course, you can find me. That's my Twitter handle there. But you can also, if you haven't already, subscribe. This is the Astronomy Cast YouTube page. So go ahead and subscribe to this one. And then you can also check out my YouTube channel, which is just search for Universe Today on YouTube and you'll find me. And also check out my Instagram. I'm having a lot of fun letting people take over a lot of amateur astrophotographers taking over our feed every day and posting a bunch of their pictures. So if you're an astrophotographer and you're on Instagram, follow Universe Today and then just use our hashtag and let me know and we'll let you take over our account and let you post some pictures. So
That's
super fun.
awesome.
Yeah, it's great. It's a great feed. Awesome. Okay, and then one last piece of news, which is that we are using this new system. This is the first time we've used Wirecast here on the Astronomy Cast show. I think we're just downright polished and smooth at this point. Big thanks to Chad sitting beside me. But we would love your feedback. So if there's anything that you would like us to do to improve the show, to kind of make this broadcast experience more professional, more of what you'd like to see, just let us know. And we would love to get that feedback and try to keep incrementally improving things. So just let us know what we can do to make this better. All right. Thanks, everyone, for watching. And Pamela, we'll see you all. I have no idea when we're going to see you next. Goodbye.
I'll talk to you later. It'll
Bye.
probably be a week from next Friday.
Sounds good. Yeah, you can.
Awkward ending.